This PhysCast will be looking at a hydrogen atom that's changing state by emitting a photon and thinking about the angular momentum change that occurs. Pause the video and read through the question carefully. Now that you've read the question, we'll begin our solution with an interpret step, where we should be able to understand, importantly, it's a particular kind of atom we're dealing with in this problem. It's a hydrogen atom, so we'll be able to use some formulae that are quite specific to that kind of atom, and we'll also be using some general ideas about the energy states and the angular momentum states in our atoms being quantized. That is, they're only allowed to have certain values, and we've got some formula that link those values. Now, in our develop stage, we might start with a quick sketch of what's happening in terms of energy levels. We've got two energy levels we're concerned with. We might call the first one E1 and the second one E2, and we can quantify those with, say, a principal quantum number. We might call the upper one there N1 and the bottom one there N2. And of course we will think about the angular momentum as well, and that's to do with a orbital quantum number L, so we might call that L1 and this one down here L2. And our atom is changing its state from this upper state down to this lower state. It's reducing in energy, and it's giving off a photon that's carrying that energy with it. And some of the important relationships we should know here for hydrogen are that the energy of a particular state N here is minus 13.6 divided by the principal quantum number squared, and that's in units of electron volts. And we should know that the angular momentum of our system, of our atom here, is going to be Planck's constant divided by 2 pi, that is h bar, multiplied by the square root of small l into small l plus 1, where small l is our orbital quantum number, and for a particular state, that orbital quantum number L can only be between 0 and 1 less than our principal quantum number. And it can only have values of 0, 1, 2, 3, etc. Something else we'll need to consider here is what's going on with the photon. The energy of the photon is also quantized, and it's given by Planck's constant times the frequency. And our question here is telling us wavelength, so we might more conveniently write that as Planck's constant times the speed of light divided by wavelength. And one other thing we might need to consider here, to do with the angular momentum as this transition is occurring, is that our photon carries off angular momentum. And so we'll need to keep in mind that there is a condition, a selection rule, that says the transitions here can only occur where the change in our orbital quantum number is 1 unit, so either plus or minus 1. In our evaluate stage, we can start a calculation where we might like to understand what's happening in the initial state of the atom, and we could use this equation right here to write down that principal quantum number in our first state will be equal to the square root of minus 13.6 divided by the energy of that state. And in this case, that will be the square root of minus 13.6 divided by, here's our initial energy, minus 0.85, and that comes out to be exactly 4, which gives us some confidence that this question has been correctly set up, because we know that this principal quantum number has to be some positive integer. So we're starting in the n equals 4 state, and we should also be able to figure out what the angular momentum is for there. We're told it's root 6 times h bar, and we know that that must equal h bar times the square root of L into L plus 1. Now we could solve that equation, because anything we don't know in there is the value of small l, and if you do that you'll end up with a quadratic equation for small l. There'll be two solutions, one of which will come out to be negative, which we can ignore because we know small l for our system has to be a 0 or positive number, or you can just examine what those first few values for capital L will be. For small l equals 0, 1, 2 and 3, and you should be able to straightforwardly see that to get root 6 h bar, this small l here in our first state must be equal to 2. So this first state here we have n is actually 4 and l is 2. Now what we're trying to understand is what happens in this lower state here. We want to find out what the angular momentum is after the photon has been emitted. So we can do a similar kind of calculation, but we need to know what this lower energy is. Well, we know that this lower energy here must be the situation where the photon has carried off the energy difference between E1 and E2. Or I can rearrange that and find the energy of the state that I'm interested in must be E1 minus that photon energy. So I can write that down. E1, remember, was minus 0.85 in units of electron volts, and I'm going to subtract off that my photon energy, which I talked about up here in my developed stage, is going to be Planck's constant. So I can know that as 6.626 times 10 to the minus 34, a very small number indeed, multiplied by the speed of light, 3 by 10 to the 8 in SI units, divided by the wavelength, and the wavelength here is 487 nanometers, so 487 times 10 to the minus 9. Now, all the quantities I've put in there are actually in SI units. That would give me an energy in joules, which I can't really combine with an energy in electron volts. So I might convert from joules to electron volts. And to do that, I need to divide by that conversion factor, which is just the charge on the electron, 1.6 times 10 to the minus 19. That will convert that value from joules into electron volts, and then I can combine it with my minus 0.85 electron volts. And if I do that calculation, and you should certainly try that yourself, I come up with an energy here. It's a negative because it's a bound state energy of minus 3.4 electron volts. And then I can do the same calculation as I did earlier to figure out what the principal quantum number is for this lower state. It will equal the square root of minus 13.6 divided by minus 3.4, and that comes out nicely also to be an integer, in this case 2. So I've gone from the n equals 4 state down to the n equals 2 state in this particular transition. But what I want to know about is the angular momentum. Now, for this particular principal quantum number n equals 2, my rule says I could have the angular momentum of this lower state equal to 0 up to n minus 1, so up to 2 minus 1, which is 1. They're my only possibilities. So I could say, well, I know that after the emission I could be in L equals 0 or L equals 1. In fact, I know more than that, because I know that the change in the small L value here has to be plus or minus 1. And I started off, remember, in the upper state with L equal to 2. So after the transition, I can only be in 2 plus 1, that is L equals 3, or 2 minus 1, L equals 1. I can't be in L equals 3, because that's not a possible value for small l in the n equals 2 state. So in fact, I must only be, I can't have this L2 equal to 0, because that's a change in small l of 2 units. It would be going from L equals 2 down to L equals 0. So in fact, I know that my final state here must have L2 equal to 1, or I must have an angular momentum of h bar into the square root of 1 times 2. So that must be the final angular momentum of my atom after the photon has been emitted. Now we can just do a quick assess step here. One thing we might like to assess is that we've actually got the right states in the first place. So one thing we could do is we could actually calculate, using the same kind of ideas we've done here before, what sort of photon we'd expect if we were going from n equals 4 down to, say, n equals 1 instead of n equals 2. And if we did that, we would find, and it's a calculation you should do, it's a fairly straightforward, using the same principles we've used here, you'd find you'd get a wavelength of the emitted photon for that transition of about 122 nanometers. And we could double check again if we wanted to the n equals 4 to n equals 3, for example. And if you did that, you'd find you'd end up with a wavelength of the emitted photon there of a bit more than a micron. You get there something like 1.8 microns, I think it is. And so we were looking, we thought, at the n equals 4 to n equals 2. That's what we thought our calculation showed us, which is consistent. Remember, we had a photon here of a wavelength of 487 nanometers, which is somewhere in between these two, which is what you'd expect if you were going from n equals 4 to n equals 2. It should be somewhere between these two transitions. So that gives us some confidence we've identified the right transition, and then we've applied our rules to come up with the right understanding of what that final angular momentum must be.